Okay. So the first application is something you should have seen already in 228, but let's see that more formally here. So what we are trying to do here is to search for a key in an array. And I already mentioned that in order to do binary search in 228, I said the array has to be sorted. If you want to search for a specific key in an array using binary search approach, the prerequisite is the array has to be sorted. So you cannot use binary search to search for a key if the array is not sorted. Okay. Now it depends again on the application. For some applications the array need not be sorted. So for this application, which is searching for a key in an array, the array has to be sorted, and you will see soon why it has to be sorted and why it cannot be some arbitrary array. So let us use this example, and we'll come back and also look at the general format for the strategy. So again, so to begin with, the search key could be anywhere in the array. So your search space is the entire array size, which is the number of elements in the array. So if you are going to program it, you need to be given the array and a search key. So in this example, let's assume the search key says some 70. Now the key could be there in the array or need not be there. So the result could be either a successful search or an unsuccessful search. And we are able to find out whether it's successful or not as part of the binary search approach. So to begin with, it could be anywhere. So let us say the left index is 0 and right index is n minus 1. So in each of these binary search applications, you will see will try to maintain what is called an invariant or a principle, in the sense that whatever our search space, here you are going to search for a key, but in general you can still call it as a search space, which is the range within which you will be working on, will be from a left index to right index. So if at all the search key is there in this array to begin with, it could be anywhere from 0 to n minus 1. So to begin with, it could be anywhere from the left index to right index, 0 and 12. Now you will shrink or reduce the problem size by half as we go in the iterations, and still will try to maintain this invariant. Okay. All right. So let us also look at the pseudo code. So left index is 0, right index is n minus 1. So we'll do the iterations or do the binary search only if the left index is less than or equal to right index. That means you want to search within a range ranging from left index to right index. So that means the left index has to be less than or equal to right index. We cannot search if the left index is greater than right index. So think about searching from index 5 to index say 4. Doesn't make sense. You can say you're searching from index 4 to 5, but you cannot say I'm searching starting from index 5 all the way to index 4. You cannot say like that. So that's why we always say left index should be always less than or equal to right index. And if that is true, you find what is called the middle index, which is left index plus right index divided by 2. So an average of left and right index. So in this case it is 0 and 12 divided by 2. So that is 12 divided by 2, it is 6. So in order to take care of the division to be an integer result, we kind of flow. So if left index plus right index is an odd integer divided by 2, you are going to get a real number with a fraction. So you have to still kind of truncate that and take only the integer part of it, because working with array index, it has to be an integer. So the middle index is the average of left and right index. So in this case it is 7. So if a search key, in this case 0 plus 12 is 12 divided by 2, it is 6. So the middle index is 6. So if the element at index 6, which is a of m, the search key is equal to the element at the middle index, that means we have found the search key, right? So if k, which is 70, is equal to the element at index 6, in this case it is 55, 70 is not equal to 55, so we cannot say we have found the search key. So we have to go to the else part. So now see, that is like the comparison. We are trying to, now we are in the process of deciding which of the two sub problems we should go further down. So the middle index is kind of like a cutoff to decide to break the problem into two sub problems, and now we are going to decide which of the two sub problems to go further down. So if the search key was equal to the element middle index, we are done. But since the search key was not equal to the middle index, we need to decide how further we have to go, which of the two sub problems to go further. So we need to decide if the search key is less than the element at the middle index or greater than the element at the middle index. It was definitely not equal to. If it was equal to, we would have stopped there. So that's why we have, if the search key is less than the element at the middle index. So if the search key is less than the element at the middle index, that means it should have been something less than 55. But we have here 70, which is greater than 55. So that means it's not satisfying the condition. The search key is, in our case, greater than the element at the middle index. So we go to this else part, and what we do here is, so if the search key is greater than the middle index, in this case that's what it is. So since our array is sorted, we can confidently say the search key will not be to the left of this middle index 6, because since the array is sorted and 70 is greater than the element at the middle index, 70 will not be at all there to the left of 55. It has to be only to the right of 55 if at all it is there in the array. So this is how you decide which of the two sub problems to solve. So you decide to solve only the right, or search for only the right subarray or right search space. So you can discard the left search space completely. You don't need to work on it further. Okay. So that means in order to do it repeatedly, we have to move. Now again, we want to maintain the invariant that if at all the search key is there, it is within the left index, right index. So since it can be only in the right subarray, we don't need to keep this left subarray. So we can move the left index to the right of the middle index, and not even at the middle index. We can move to the right of the middle index because the search key was not equal to the element of the middle index. So that's why I say left index equals middle index plus 1. So left index takes up 6 plus 1, 7 as its value. And the right index stays as it is, because at any time we can move only either the left index or right index. So here we are moving the left index to the right of the middle index. So that means we are still on the right subarray. So the right index stays at 12. And that's the process. So we now repeatedly do this by checking if left index is less than or equal to right index to continue further. Here, yes. So we will go further and find the middle index to be 7 plus 12 divided by 2. So here we have 19, which is an odd number. So 19 divided by 2 is 9.5. So we truncate and use 9 as the middle index. So now we need to compare our search key 70 with the value at index 9, which is 81. And 70 is not equal to 81. So we have to go further and decide which of the two sub problems to solve in this subarray. So we check if 70 is less than 81, and it is. 70 is less than 81. So that means if at all 70 is there, so if you visualize this, so in the first iteration we discarded this portion. So now we are going to work only on this portion. And we now decided 70 is less than 81. So if at all 70 is there, it cannot be at 81 or to the right of 81. It can be only within this narrow range. So the left index is 7, but since we are going to discard the right subarray as well as the middle index portion, we have to set the right index to be 1 less than the middle index. So we say right index equals middle index minus 1. So that means right index will be 9 minus 1, which is 8. So you see how we are reducing the search space. So now continue with that, and again the left index is still less than or equal to right index, 7 less than or equal to 8. So the new middle index is 7 plus 8 divided by 2, which is 7. So now compare the search key 70 with the value at the middle index 7. So we also see 70 there. So they are equal. So we can say we have found the search key and return M, which is the index where the search key is. So with that, this code will stop. Okay. So far, any question before you go further? Okay. Right. So let us continue with the time complexity analysis. So if you look at now the general recursion, it is T of n is 1 times T of n over 2 plus f of n. So it is this f of n we need to decide, and we can say the basic operation is simply this comparison. We are comparing the search key with the value at the middle index, and then deciding whether to go further to the left or not, or if they are not equal. So how many comparisons we are doing? So we can say C of n is the number of comparisons to search in an array of size n, breaking into two sub problems but solving only one of them. So and f of n is how you decide which sub problem to go further. And in order to do that, how many comparisons you are doing. That's a basic operation. So we are comparing as part of the logic first whether they are the same, and then if they are not the same, you need to decide whether it is less than the middle index value or greater than. So we need two comparisons. So that's why we are doing two comparisons. One is the equal to based comparison, and the other is the less than comparison. Okay, so the two comparisons you are doing for our f of n, and that is for n greater than 1. If n is equal to 1, that means you just have a search space of just one element, and you want to check if the search key is there. You just compare the search key with that one element that is there in that subarray. So that will be one comparison. So that is how you write the reconciliation. For n greater than 1, this is the reconciliation. C of n is C of n over 2 plus 2. And if n is equal to 1, you do one comparison. So we can use master theorem to solve this. We can also use the other approach that we saw in module 1 to solve this kind of reconciliation, but we'll use master theorem. So for that, we need to write this f of n as some theta of n raised to d, and this is a constant. Okay, so which means irrespective of the array size, we still do two comparisons per step to decide which of the two sub problems to go further down. So you see now the constant time complexity. So your array could be of 1 million elements, and you break that into two arrays of size 500,000 each, and you still decide you need to do only two comparisons to decide which of the two sub arrays to go further down. So it's always a constant time complexity. So in this case, so that is 2, which is theta of 1. So d is 0. Because theta of 1 is theta of n raised to 0, so d is 0. So b raised to b is 2 raised to 0, and that is 1. So a is equal to b raised to d. So c of n is theta of n raised to 0 log n raised to d log n, which is theta of log n. And we saw that's what, as a general thing, if d is equal to 0 and that means f of n is equal to theta of 1, the overall time complexity of binary search would be simply theta of log n. Okay, so when you go for interviews, they may try to find out if you get to know this. So if you spend constant time in binary search to decide which of the two sub problems to solve, the time complexity is simply theta of log n. Okay, so this is not only for this problem. So in general, for any binary search based solution, if you spend constant time to decide which of the two sub problems to go further down, you don't even need to write all these reconciliations and find out the time complexity. You can right away say the time complexity is theta of log n. Okay. Now let us do an unsuccessful search and see why this invariant needs to be always maintained for a successful search. Now let us say we want to search for say 10, which is not in the array. Let us see how it is going. So we'll start with left index as 0, right index as 12, so middle index is 6, and we're comparing 10 with the element of the middle index, which is 55. So 10 is not equal to 55, so we need to decide whether to go to the left or right, and 10 is less than 55. So that means we can, if at all 10 is there, it has to be only to the left of 55, not to the right of 55. So that means since it's not equal to 55 and it's less than 55, we can discard the right subarray, the search space. So you see the left index will stay at 0, but the right index has to be now m minus 1, so it is 5. So that is now a right index. So the new middle index is 0 plus 5 over 2, which is 2. And you are now comparing again 10 with the value at the middle index 2, which is 27. They are not equal, and 10 is again less than 27. That means if at all 10 is there, it has to be to the left of that 27. So that means we can again discard this search space ranging from the middle index to the right index. So again we will be reducing the right index further down. So you always see the left index moves towards the right and the right index moves towards the left, and they will try to eventually meet, and by the time they meet, if at all the search key is there, we should have found it. Okay, well, let us see what's going on. So the right index has to be now set to again m minus 1, so it is set to 2 minus 1, which is 1. So the search space is now from 0 to 1. So the new middle index is 0 plus 1 over 2, which is 0, and the value at index 0 is 3. So combine the search key 10 with 3. 10 is not equal to 3 and 10 is greater than 3. So if at all the search key is there, it has to be to the right of the middle index. So that means we have to discard the range to the left of the middle index as well as the middle index, which is just this one element here. So this is our search space of just size 1. So the left index is set to middle index plus 1. So it is 0 plus 1, which is 1. The right index is also 1, and the new middle index is 1 plus 1 divided by 2, which is 1. So that's just one element. So we have to do just one comparison, and 10 is not equal to 14, right? So if you want to decide how to go further down, see right away, you can decide, since 10 is not equal to 14, is not there. But as part of the general logic, let's see how the algorithm is terminating. So 10 is actually less than 14. So if at all 10 is there, it has to be to the left of middle index. So in that case, we have to move the right index further to the left, right? Because there's no point in staying at 14 or right of 14. 10 is less than 14. So move the right index further to the left. If you try to move the right index further to the left, it has to be set to middle index minus 1. So that means middle index is 1, minus 1 is 0. So right index becomes 0. And you see now the left index has become greater than the right index, and that is when the algorithm will stop, because you see the pseudocode, you do all these things when the left index is less than or equal to the right index. The moment the left index becomes greater than the right index, you have to stop. Okay, and that's how you analyze the algorithm, and this is for unsuccessful search. Okay, and so any question on binary search? Searching for a specific key. Okay, so let me save this.